Today we're going to find confidence intervals for means. Remember, for confidence intervals for proportions, we use p hat plus minus z star times the standard error of p hat. We used a z for critical value because the central limit theorem told us the sampling distribution model was for proportions is normal. We want to do the same thing for means, and the central limit theorem says that sampling distributions for means follow the same normal model, except remember your mean is the population mean, and your standard deviation is the population standard deviation divided by the square root of the sample size. So to use the CLT for the sampling distribution of x bar, all we need is a random sample of quantitative data and the population standard deviation. With proportions, we had a link between the proportion value and the standard deviation. This is what this is referring to, right? Instead of P and Q, we use sample proportion and failure proportion. But for means, we know the standard deviation is sigma over the square root of n. So knowing our sample mean doesn't tell us anything about the standard deviation. So what did they do back in the day? Well, they did what anyone would do. They estimated the population standard deviation with the sample standard deviation. So this is what we will be doing. William Gossett first investigated this. If you're interested, you can look him up. And we'll move on. We use Gossett's model with n-1 degrees of freedom denoted as df. When certain assumptions and conditions are met, the standardized sample mean. To find our t value, we take t sub degrees of freedom equals the sample mean minus the population mean over the standard error of the sample. It follows the student's t model, and we estimate our standard deviation with the standard error of x bar is the sample standard deviation divided by the square root of n. When certain assumptions and conditions are met, the confidence interval for mean is the x bar plus minus the critical value t star times the standard error of the sample mean. On your formula sheet, it says confidence interval is statistic plus minus critical value times the standard deviation of the statistic. That is what I would remember. I would not really focus on the formula. The reason being is if you write down the formula on the AP exam and you forget a symbol like the bar over the X or the star next to the T, they will dock you. The critical value T depends on a particular confidence interval C and the number of degrees of freedom which we get from the sample size. This link will take you to a video analogy of what we mean by confidence interval. So, in our next example, in 2004, a team of researchers published a study of contaminants in farmed salmon. Fish from many sources were analyzed for 14 organic contaminants. The study expressed concerns about the level of contaminants found. One of those was insecticide Murex, which has been shown to be carcinogenic and is suspected to be toxic to the liver, kidneys, and endocrine system. One farm in particular produced salmon with very high levels of Murex. After those outliers are removed, summary for the Murex concentration in parts per million in the rest of the farmed salmon as follows. The N is the 150. I think in your note packet it says 159, so make sure you change that. X bar is 0.0913 parts per million, and the standard deviation is 0.0495 parts per million. And the question says, what does a 95% confidence interval say about Murex? Remember the 4 steps. First step, state. This is where we state the parameter of our estimate for the confidence interval. So our state, mu is the mean Murex concentration in farmed salmon. Then we go to our plan step. We're going to identify the inference method and check our conditions. So for our plan step, we're using a 1 sample t interval with degrees of freedom 149. It's 150 minus 1. Because we don't know anything about the conditions specifically, we just assume the conditions for inference are met. Next, we're going to go to our do step. Note, we took our sample mean plus minus our critical value 1.976 times our standard error of the sample, and we get approximately a lower end of 0.0834 and an upper end of 0.0992. Now, the t star kind of varies depending on which method you use to find it. Okay, you could hypothetically run the interval in your calculator, and then you don't have to worry about really writing a critical value. Usually I'll just leave it as T star. You could use your table if you flip to table B in your formula packets. The table in the textbook will go to degrees of freedom 140. If you're looking at the table in the formula packet provided from the College Board, the closest degrees of freedom is 100. And I believe for that one, the critical value is 1.984. Or you can use inverse T. Remember, for a 95% confidence interval, we want the middle 95%. So if 95% is in the middle, then that means on either end you have 2.5%. So you'll do inverse T 0.975, comma the degrees of freedom, or 149. 1.976 is the critical value using the calculator. And then we're ready for our conclude step. We are 95% confident that the mean level of murex and farm-raised salmon is between 8.34% and 9.92%. Not percent, parts per million. That's a typo. That's annoying. And we done. For our assumptions and conditions, there's no way to check the independence assumption, but you can decide if the assumption is reasonable. I'm not specifically going to ask you about the independence assumption in any assessment. I'm primarily looking for these three: randomization 10%, nearly normal / large enough / large counts. Okay, so random, obviously the sample has to be random, or assume it is to be representative. Remember, for 10%, the sample is no more than 10% of the population. In nearly normal, this one is different from proportions. Remember when we talked about sampling distributions? For nearly normal, if our sample is already larger than 30, then we can assume by the central limit theorem that the model is approximately normal. Now, if you have a sample that is less than 30 and you have all the data values, it is required that you either show a stem and leaf plot or a histogram or a dot plot to verify there's no severe skewness and the display is fairly symmetric. This N is less than 15. The data should follow a normal model closely. In between 15 and 40, the model will work reasonably for symmetric distributions, and for N is greater than 40, the T methods work unless the data are extremely skewed. We don't really do a whole lot with that. We primarily focus on 30. So back to the murex example. Again, researchers purchased whole farm salmon from 51 farms in 8 regions in 6 countries. The histogram shows the concentrations of the insecticide murex in 150 farm-raised salmon. Are the assumptions and conditions for inference satisfied? Well, independence. Well, if salmon were raised in different farms and samples were purchased independently from several sources, that should be okay. Random. It says in our story, well, we're going to assume that the fish were randomly selected from those for sale. 150 is less than 10% of all farm-raised salmon. And for nearly normal, they provide us with this nice histogram. So if we look at the histogram, it is unimodal and slightly skewed to the right, but a sample of 150 is large enough to assume approximately normal. We can use inference. Now we're going to look at another example. We have Christina and Rachel randomly selected 18 rolls of generic brand toilet paper to measure how well this brand could absorb water. To do this, they poured a 1/4 cup of water onto a hard surface and counted how many squares of toilet paper it took to completely absorb the water. And here are the results of their 18 rolls. We're going to construct and interpret a 99% confidence interval for mu equals the true mean number of squares of generic toilet paper needed to absorb a 1/4 cup of water. Okay, remember our first step is the state step, where we state the parameter you want to estimate in the confidence interval. So our mu this time is the true mean number of squares of generic toilet paper needed to absorb a 1/4 cup of water. Next is our plan step. Remember, we're going to identify the inference method and check our conditions. So our inference method is called a one sample T interval. Now, if we go back to the previous slide, we need to figure out how many degrees of freedom that we have. It looks like we had 18 rolls of toilet paper, so that means our degrees of freedom is 17. The next thing we have to do is we have to check our random condition. It's stated in the question that Christina and Rachel randomly selected 18 rolls of generic brand toilet paper. 10%. 18 rolls of generic brand toilet paper is less than 10% of all generic rolls of toilet paper. And this time, because we had all of the data values and the sample is less than 30, we have to show some sort of graphic display. You could do a stem and leaf plot, you could do a histogram, you could do a dot plot. I had my calculator create a histogram, and notice our bin size was 2, and this first bin was 3 units high. Now, based off of that histogram, the sample is small, but the histogram shows no small skewness. We're going to assume it's safe to proceed. The next step is our do step, and that's if our conditions are met, we are going to perform our calculations. So notice if I type all those into my calculator and I run one variable stats, we should get a mean of 29.944, standard deviation of x 2.859, n is 18, which means our degrees of freedom is 17, and our critical value is 2.898. Again, I can find that using my chart, going down to 17 degrees of freedom, and 99% confidence should give me a critical value of 2.898. Now we're ready to set up our interval. So if we go into our interval, notice we start with our sample mean, plus minus our critical value, times the standard error of the sample. So if our sample standard deviation was 2.859, we divide that by the square root of 18. And we should get a lower bound of 22.991 squares and an upper bound of 26.897 squares. If I wanted to run this interval in my calculator, I definitely can. I can either set it up as t interval with data, and because everything is in list 1, I just select the confidence level and then run the interval, which as we can see is very close. Notice it also gives me my x bar, my s of x, and my n equals 18. Now you could have highlighted stats and just used all of the sample statistics we found using one variable stats. Your answer will be slightly different, but close enough. And then last but not least, we're going to conclude. We're going to interpret our interval in the context of the situation. We are 99% confident that the true mean number of toilet paper squares needed to absorb a quarter cup of water is between 22.991 and 26.897. Now let's talk about sample size. To calculate the appropriate sample size for the data collection, we can do the following. Remember, margin of error is going to be our critical value times our standard error. But we don't have most of the values to solve. Like, the critical value is strange. We need to know the sample standard deviation, and we don't know it until we collect data. If we don't know n, we don't have degrees of freedom, and we can't find t star. If using a 95% confidence interval, use the 68, 95, 99.7 rule if your sample size is large enough, meaning approximately 60-ish. It's probably okay to use a z-star. So in our last example, note it says a company claims its program will allow your computer to download movies quickly. We'll test the free evaluation copy by downloading a movie several times, hoping to estimate the mean download time with a margin of error of only 8 minutes. We think the standard deviation of downloaded times is about 10 minutes. How many trial downloads must we run if we want 95% confidence in our estimate with a margin of error of only 8 minutes? Okay, so it says we'll test a free. We're going to use z-star just to get started. And if I use z-star and I want 8 minutes as my margin of error, I set up 8 equals 1.96 times 10 over the square root of n, since we don't know our sample size. When we solve for n, we do get approximately 6.0025. Okay, so what that means is this is a small sample, so we're going to use 6 minus 1, or 5 degrees of freedom, to substitute an approximate value of t star. Okay, so I can use my chart if I want. Chart degrees of freedom 5 with 95% confidence, or you can use inverse t 0.975 comma 5. From there, I should get a critical value of approximately 2.571. So 8 equals a critical value times 10 over the square root of n. And we solve for n to figure out our sample size. And it looks like we have 10.328 approximately, which remember we always round up. So to get a margin of error of 8 minutes, we're going to find the downloading time for 11 movies. Yay, we finished the notes. Practice time.